Hi, this is a video for compiler design, COMP442 and 6421. This is for week 7. So at this point in the project, we are at a point where we have generated an abstract syntax tree doing syntax-directed translation. So in the next phases, the following two phases or few phases of the project, we are essentially going to traverse the abstract syntax tree and then do some implement some semantic actions that are going to implement the following phases, like symbol table generation, semantic checking, and eventually code generation. So now today I'm going to explain how you can do this abstract syntax tree traversal and inject somehow the semantic actions at the right places in the traversal so that you can do at this point symbol tables and creation of symbol tables and semantic checking. Now, this is all going to use, as I propose it, it's going to use, as I explain it, it's going to use the visitor pattern. You don't have to use the visitor pattern, but it is one of the patterns that I find is most among all the different kinds of patterns and their uses that I've seen. This is one of the most striking ones. It seems that the visitor pattern was made to actually achieve exactly the goal that we have in mind for this particular task. So that's why I chose to explain that, and I actually found that from the book by Leblanc and Citron. Compiler design book by Leblanc and Citron. Okay, so let's go to the slides. Okay, good. Okay, so so here what I'm going to do is I'm going to explain what is the symbol table, and then how you can actually generate it, or imagine how it's actually generated as the program is being traversed. In our case, I'm going to assume that it's going to be done by traversing an abstract syntax tree. You have to understand it can also be done doing syntax-directed translation. So as you did for the generation of the AST, you had to do syntax-directed translation to inject semantic actions to actually generate the tree. If you would not have a tree, you could actually inject semantic actions to generate the tables, then inject other actions to generate, to do the type checking, and then inject other actions to do the code generation. Difficulty with that is that you are packing up, you're loading up your parser with more and more and more semantic actions. And at some point it becomes very hard to manage, especially if you want to have different phases. Then sometimes you need to retraverse the program because some phases depend on the operation of another phase. So as soon as you start having the necessity of compilation phases, starting after the parsing, then if you're doing syntax-directed translation, you basically have to reparse a program over again, or turn off the parsing. But anyway, it's become much more complicated if you're doing all of this using syntax-directed translation. Okay. So here, that's why the assumption I make here is that you have an abstract syntax tree, and that what we're doing here is we're traversing the tree after it's been generated by the front end, which is driven by the parser. Essentially here, what we're doing, what we're starting doing here, if we have an abstract syntax tree, we're basically building a backend to the compiler that is taking the AST, traversing this AST potentially many different times to actually do the further processing as the backend is doing, as we saw in the previous, the first video in this course. So first, let's give some context here. So here we're using a particular kind of programming language. So we're using a language essentially that is manifestly typed language. What does that mean is that the type of the identifiers that we are using is defined or declared in the program itself. So if you're using a variable in this language, you have to declare what's the type of this variable. Declaring a function, you have to declare what's the type of each of its parameters and what is its return type. So the type information is part of the program. So that's what's the meaning of manifestly typed languages. So all the discussions that we're going to have here are going to be taking this for granted that we are using manifestly typed languages. There are other languages such as dynamic languages. Just for example, JavaScript is not a manifestly typed language. Now, some people say, well, I'm going to use JavaScript because it's so much easier to use and so on. It doesn't use types. Types creates all sort of problems for me when I do my programming. So I'm going to use a language that does not use types and that's going to make my life easier. Well, if you try to do that and you try to execute your programs, then you realize that what the problem is going to happen, the problem is not going to be at compile time anymore. The problem is going to be delayed to execution time, which is creating even more problems. Okay, so some people think, well, having the types out of the program is making your life easier. It's not. It's just going to delay the problems to the execution time, which is actually even worse. Because that does not mean, in terms of compiler design, then actually what that means is that if you don't have types in the programming language, then in fact you cannot do many of the checks that are about type checking. Some of them you can do by doing type inference in expressions and so on. But there are many things you cannot check. You just cannot check at compile time because the types are not stated in the program. Now, that does not mean that you will not have to make these checks. What that actually means is that you're not doing them now at compile time because you can't. You will only know some of these types that are not in the stated in the program. You will become to know the types of values that are being manipulated only when you execute the program. And then you will have to make the checks before you execute the code, or else the program will fail as it's being executed. So what that means is that all these checks that you're not doing at compile time, they're not in the compiler. They're not made by the compiler. They're actually made by the runtime system. So you see that you actually transfer the complexity of the checking from the compiler and you transfer it to the complexity of the runtime system. That's one of the reasons why dynamic languages like this, they inherently execute somehow slower than compiled languages. Doesn't mean that they're easier to implement because they don't have types in the programming language itself. It just means that all these checks have to be made at runtime. Okay, so that's about it for this discussion about manifestly typed languages versus what we call dynamic languages nowadays. Some people think dynamic languages are new. No, they are not new. Actually, some of the first programming languages were actually of this kind. Many things in computer science that people think are new, they are in fact not new. It's just an older idea that has become a new trend. So what is the objective? So one of the objectives of a compiler is to verify that your identifiers are properly used according to their specifications of what they should be used as. So that's why in a manifestly typed language, it becomes very apparent, very clear what is the type of a variable and what is a normal use of a certain variable and what is an illegal use of a certain variable. That enables you to make these checks at compile time. So variables would have their variable declarations, the type of the variable, the dimensionality of the variable, The functions are specified using a parameter list that includes the type and a return specification type. So then you can actually, when you have a function called semantically in the code, then you can actually check if it's used with the right number of parameters and the right type of parameters. In many cases, not necessarily all, especially if you have polymorphism. And polymorphism has to be something that is delayed at runtime. In our case, in the language that we don't have polymorphism. We have inheritance, but without polymorphism. If we would allow polymorphism, they would have to be done at runtime. And in this course, I chose to make most of the complexity is going to be in the compiler, and the runtime system is going to be extremely minimal. Okay. I want to concentrate on the compilation process and not necessarily go into complexities of the runtime system. We will still have a stack operated mechanism when you call functions and so on, but that's going to be about it. In real life, of course, runtime system is going to be much more complicated than what we will end up having in the project. There's also the issue of scoping. In all programming languages, when you declare a variable or an identifier, it's defined in a certain scope. So you have to make sure when an ID is used, that it is actually defined in the scope in which it is used. In languages where you don't declare variables, then it has much more freedom to use identifiers freely. Some languages even force you to declare a variable, but not necessarily by declaring the type of the variable. In our case, we use manifestly typed. So anytime you use a certain ID, it's assumed it should be defined inside the scope in which you use it. Okay, so that's it about the contextual description of the context in which we are operating here. You see that depending on what languages, what kind of language you're using, there is different issues involved and different focus at different phases of either compilation or execution of the program. In this course, we're using manifestly typed. It's not necessarily what is happening in all different kinds of languages. Okay, so how is this processed? This is the point here of this lecture, is to explain how these things are processed. Well, how you, for example, how do you figure out if a variable has been declared? When you use a variable inside a function, for example, how do you figure out if it has been declared before? So it means if you are to be able to do that, you need to have some kind of dictionary for the current scope that has an entry for every ID that is valid in this scope. So how do you do that? So first of all, declarations are processed as the tree is traversed. So you have your abstract syntax tree, and then for each of the concepts, you have a subtree. For example, for a class, you have a subtree. For a function, you have a subtree. I have on the board behind me, you may have noticed I have something. I'm just going to go here just to give you an introduction of the concept. So in this case here, what I have is a function definition tree. So all of these here, this, and this are all children of a function definition. So that's the name of the function. That's the function of formal parameters of this function. So that's the list of parameters of the function. And this is here the list of variables that are declared inside of this function. This particular example here is using this same notion that we have in the programming language we have this year in the project, where you have this var block at the beginning of any function that includes all the variables that are declared and usable in this function. So that's my var_dec subtree here that contains one subtree for every variable declarations that is in this var block. Then after that, then I have my statement block for the definition of the operation of this function. For example, you might have a certain ID that is equal to an ID times ID. Okay. So that's basically a statement that I have in my function. So eventually, as I'm going to process this, for example, A is equal to B times C, then when I come to A here, then I should be able to figure out if A is a valid identifier for this scope. So how would I know that? Then essentially what I want to achieve is to have this symbol table, which is essentially a dictionary of entries, and each of these entries are defining an identifier that is valid inside of the scope of this function f1. Okay. So as I'm going to traverse this tree here, one of my goals is first going to be to create this symbol table. Okay. First of all, so that when I come here and I see, for example, A, then I will ask myself, is A valid? Or for example, well, first of all, is A valid in this function? And then if I want to do the type checking of this entire statement here, for example, if A is an int and B and C are floats, then arguably I cannot assign a float to an int. Okay. So I have to do some type checking. I also, for example, if I have X is equal to A plus B, and then X is not in my table, then I will be able to say X is undefined or undeclared in this scope. Okay. So you see that here, the type verification here that the verifications I have to do when I encounter IDs in expressions and statements take for granted that the symbol tables have already been filled up. Okay. So that's why there is actually some precedence over some of the operations that I'm doing. First, I should traverse this whole tree, construct the tables, then I should retraverse the tree and then check if the statements are correct, taken for granted that I've already have the symbol tables. Okay. It is, in some cases, possible to do all of this at the same time, but not always. There are some cases where you must have what is called different phases, because some phases really depend absolutely from prior processing to have been done. In this case, you would have to separate really in different phases. That's where it becomes much more complicated. In real life, modern compilers have literally dozens of phases. So basically, you compile your program, it generates this AST, and then you have dozens of phases that traverse the AST over and over again, doing lots of different for example, generating the tables, doing the type checking, especially for code generation. There's a lot of phases that are involved. So you have to, in real life, be able to deal with several phases. In our project, what I will propose is that you have three phases, one for generating the tables, one to do the type checking, and then another phase to actually do the, at least one phase to do the code generation. Okay. So going back a little bit, let's focus on the generation of the symbol tables. So here that basically is saying that when I have my function definition node, there should be attached to this node, there should be this table here. So that's first of all taking the assumption or assuming that there will be some data members that I will add to my AST nodes. Okay. So that's what's going to happen as you will create semantic actions. They will somehow force you to add new data members to your nodes. For example, some of the nodes will have a semantic, a symbol table. Then, so function definition has a table. Then there will be other nodes. For example, this one here for the f params, the f params list of this function. Then as soon as you encounter one of the formal parameters, then eventually for example, if you say that this parameter, this function receives a parameter a, which is an int, then what that means is that in this function, in the body of this function, you can now use this variable I, which is an int. What that means is two things. So as you process this parameter subtree, the subtree for this parameter, then you must somehow assemble a symbol table record as you traverse this tree here. For example, to store that there's a variable I here, its name is I, and its type is int, and then potentially it has a list of dimensions. Okay, it's going to be a record, symbol table record that you're going to create as you traverse this tree. And eventually, as this one will come back after its old subtree has been traversed, then this one will actually go and fetch these records here, these symbol table records here, and will actually put them inside of the table. Then, of course, for the variable declarations, any variable declaration you have inside of the var block, they will each, as you process each of them and their subtree, you will actually create another such record. So this one will have its own record as you traverse the tree here. So when you get out of here, this node here will now have one of its data member is going to be this record that has been filled out as you traverse the tree. Then you go to the other one, and then you do the same. So then you have, for each of the variable declarations you have in your var block, each of the top nodes here will have one such record, so that when the function definition has finished traversing the whole tree, then what it will do, it will go here, get this record here, put it in the table, and then we'll go here, get this record, put it in the table. We'll go here, get this record, put it in the table, and so on and so forth, so that at the end of this whole traversal of the whole subtree of funcdef, then funcdef will have a table that has been filled in with all the records that it found inside of its subtree. Then after, you will do another pass that will actually do the semantic checking, so that in the other pass, it will concentrate on, for example, the statements. So when it sees the statements, then it will have other semantic actions that will fire, that will, for example, when you have an assignment statement, you will have some semantic actions that will check if the type of this is the same as the type of this. If what you have to the left and the right of the assignment is actually the same type. If it's not, then it will give an error. Same thing will happen for a times node. So when you have two operands to a times operation, the assumption we will make here is that they must be of the same type. And if they're not, then it will throw a semantic error. So you see that these are semantic actions that are fired as you traverse the tree. Just exactly the same concept as you had here, except that here, the semantic actions that were fired were about aggregating information and putting it all in the table. And then these other ones here, which are done after in another phase, they will actually use the table here in order to make the semantic checks. Okay. So how you see that there is a precedence relationship between the operation of these semantic actions here and the operation of these here. These must be done all before these, because these here require the result of these here. So that's what is the whole idea here. I hope that was clear. So let's go back to the slides. Something's wrong. Okay. Did I have, or did I skip the slide? No, it's later. Sorry. So, symbol table structure. I have explained that a little bit in the video for assignment number 3. So maybe you want to complement what I'm going to say here with what I said also in the statement of assignment number 3. Hopefully what I'm going to say here is going to be a superset of what I said in this other video. So the idea is that, as I explained here, you have scopes. So for example, here you have a function definition, which defines a scope. And when you're using variables inside of this scope, then you should verify if these variables that you are using here are valid inside of the scope of this entire function. So one of the central concepts of almost any programming language is this notion of scope. In general, in languages like the one that we have, so the syntax I have decided to use is use the squiggly brackets. Yeah. In many languages, when you have open squiggly bracket, close squiggly bracket, that actually defines a scope. So, of course, there is the global scope, which is the scope that is not included in any of these brackets. Okay. So even if you have a language that does not have scope, it would still have, of course, the global scope. Okay. So the global scope contains an entry for all the identifiers that are declared outside of any inner scope. Okay. Essentially, the global scope is the parent of all the scopes that are defined inside of it. That's why if you have a language that doesn't have scope, it has only one scope. But then that means that everything that would be defined in this language would be in the same scope, which is of course creating some organizational problems. Like when you use in a programming language, when you use global variables, if you use too many global variables, it actually tends to make your program much complex to manage. That's why, historically speaking, people very early in the history of programming languages came to the decision that scoping was a very important feature to have in order to have better possibility of good organization of programs. Then you have some different scopes, if you have them. Some scopes are named and some scopes are not named. So let's go with the named scopes. For example, when you have scope like this is a scope for a function. A function has a name. When you declare a function, you give a name to the function so that you can refer to a name when you actually call this function. So that essentially here, the scope that is associated with the function is a named scope. And the name of this scope is the function name. Other scopes that are a name scope that you may have is a class. When you declare a class or a data structure, you are defining a scope and you're defining members of a class. You're defining IDs that are valid inside of a variable of this kind. So you have, again, creating a named scope. So for every of the named scope, you would have, as I explained here, this function, let's name it F here, would have its own dictionary or symbol table for this named scope. You would have the same notion for a class, for every class that you have in your program. And then eventually, as we will see, if you have member functions, then a member function would have its own scope, which would be a subscope of the class to which it belongs. So in this case, you would start having 3 levels of abstraction of different symbol tables. I'm going to come back to that later. You may even have some scopes that may be not named. So here we have the scope that we define here is essentially the block of code that is defining this function. Okay. And more simply speaking, this is a statement block that you use to define a function. Now, there are also statement blocks. For example, if you have an if statement or a for loop, then you have a statement block that is attached to a for loop. So because it's a statement block, you might say, well, it uses this squiggly bracket, so I'm going to say this is also a scope. In reality, the languages would always define, yes, a subscope for each of the statement blocks that you declare. In the project, you could do that also. It's not going to necessarily make it complicated for now. For the generation of the tables, it's going to be a little bit more complicated if you do that, but the real complication will come as you actually do the code generation later. Okay. So I would advise you to not create subtables for inner scopes inside of a function. This is how it's done in real life, but I would advise that you don't do that for the project. It's gonna create complications later in the code generation. So you have global scope. That's essentially an unnamed scope that all programming languages have. And then you can have named scopes, for example, classes and functions, and you can have unnamed scopes. Unnamed inner scopes, which can exist also. Now here, what we want to do is to create symbol tables. So as I said, essentially a symbol table is a dictionary. Well, you can implement this as you want. It can be a hash map or a map or whatever you want. But this table needs to have some operations. So for example, you should be able to insert inside of the table. So if you want, for example, as you're going to be scanning your tree and finding some of the entries in the table that correspond to your variable declarations, you want to be able to insert them here. Okay. So you need to have an insert function to your, for example, class, which is a symbol table class. Now, one of the things is, of course, you may, for example, let's say there is a parameter named x, and then I define in my var block, I define another variable x. So here, as you traverse the tree, you're going to actually want to take this record here, x, and put it here in your dictionary. And eventually you're going to come here and come up onto this other variable, which has their record. And then you're going to want to insert here. And if your insert function is done well, then it should actually complain that X is already defined. So right now, this is actually some kind of semantic checking that you are making, checking that two identifiers with the same name cannot be declared inside of the same scope. So yes, there is going to be some semantic checking that you are going to do as you are actually doing the symbol table creation. Okay, and then when you search, there has to be a search function, because eventually as you are going to do these operations here, the semantic checking operations. So for example, you're going to be inside of this assignment here, you're going to see this variable x here. So you're going to be want to be able to see if x is defined, declared in this function. Then that's why you're going to use the search function of the symbol table. Of course, if you go and search for x, or let's say search for A, and you go in the table and it's not there, then it should say, another semantic error, should say A is undeclared in this scope. So again, there is some features that you need to implement for this symbol table. Some of them will do some of your semantic checking. Note that it's possible also when you do, for example, a search. So in this case, for example, let's say this function, let's say it is a member function of a class. So as we will see later, when you do the search, if this is a member function of a class, and let's say you see A here, so if A is not defined in this function, then maybe A is actually a member of the class. So not only you have to search in this table, you also, if you don't find here in this table, you have to look up in the parent table. Okay. So your search function should actually allow you to search in the parent table. So search is one of those kind of involved, more involved features of the symbol table. Printing the symbol table, as I explained in the video for the assignment number 3, you should have a print function that will allow us to allow you to actually print out in the file, the output file. One of the output files I'm asking for is that you print out a text vision of the view of the symbol tables in the program. So that's what would be this print function. Then, of course, you may want to be able to delete some of your tables because some of the tables, when you get out of the scope, for example, if you are, imagine that you have a symbol table for a function. Okay. Symbol table for this function is only valid or meaningful when you are inside of this, when you are processing this function. Why? Because it's impossible that when you are outside of this function that you would be able to refer to the variables that are declared inside of a function. Okay. So when you're finished processing a function, you can actually delete the table. Not that I'm going to be picky about these, but in real life, of course, if you want to save memory, if you're compiling humongous programs, memory consumption is of the essence. But in our case, we're not going to run out of memory compiling our little programs. Now here, here's an example of a symbol table. So this is an example of a program. It's not exactly the same syntax as we have this year, but it's essentially the same concept. You have classes. Classes have data members. They have member functions. And you have the program function, which is the equivalent of our main function. And you have the free functions. Now you have the global symbol table for every of the things that are declared at the global scope. That's the class declarations and the free functions and the main function. Each would have an entry in the dictionary in this symbol table. Then each of these entry would contain the specification of this particular, the outwardly useful specifications of this ID that you will need to have in order, for example, to make some semantic checks. For example, if you end up calling function 1 inside of this scope here, then you have to know if it's a valid call to function 1. How would you know that? Because function 1 has 2 parameters, which are specified. The type is specified here, and then it has an output, a value, the type that is specified here. So all this information is stored in the record, so that when you call a function, is this function called? No, it's not called in this example. So if eventually, if I would be calling function f1, let's say in this function here, then I would have to check if the call is actually valid. And of course, the way to check it is to check if it's called with the right number of parameters, right type of parameters, and if it returns the right type of value in the function call versus what it's supposed to be called with. So your entries must contain all the information that becomes necessary to know in order to make checks as to whether or not they are used properly, semantically speaking. And each of these here, in our case, all that can be in the global scope is things that have their own scope. For example, in our language, you cannot have a variable declaration in the global scope. Okay. So that's why every of the entries in the global scope each have their own symbol table. So my free functions have their symbol tables, and my classes have their symbol tables, and my program function has its symbol table. And then for each, for example, in my program function or my main function, I have one entry for each of the variables that are declared inside of my main function or program function. Then in my class, let's say class 1, there is, yes, these data members that are declared here, but there is also these two functions, member functions, that are declared here, much like these free functions are declared here, except that here these are functions that are declared inside of a class. So you see that there's much resemblance in the structure between a free function versus a member function. It just happens that a free function is a function record that is inside of a class symbol table instead of being at the level of a global table. Then, of course, for each of these member functions, they each have their own symbol table. That's eventually what the kind of structure that you're going to have to create. Okay. And these are all these symbol tables are going to be stored inside of your AST nodes. Just like in my example here, I had this function definition AST node that had this symbol table as a data member, and then which was described using the mechanics I described before, would eventually be this table would be created and then filled in with all the records. And then eventually, if I would have eventually I would have the same kind of subtree here, but for my class, let's say this function might be a member of a class up there. So then my symbol, the class node would have itself a symbol table for this class. And then this symbol table here would somehow become a child, or there would be a pointer to actually from the class symbol table to this symbol table here for this particular function inside of the class. Okay. So as you're traversing the tree to create the symbol tables, you would eventually end up creating a data structure just like what is shown in the slide. Okay, except that these symbol tables and the entries and so on, they're all residing in some of the nodes, but they are connected together by the operation of the phase that you are currently running. Now, let's go to symbol table generation. So what I'm going to show here is essentially how you are going to use the visitor pattern to do abstract syntax tree traversal. Okay. So that's the solution I'm explaining. That does not mean that's the only solution. It's a very potent solution. It actually used in many real-life compiler implementation nowadays. Again, does not mean that's the only solution. It is using the visitor pattern. Visitor pattern is an object-oriented pattern. So if you're using a language that does not have the same features as the object-oriented features that this pattern is requiring, then maybe you will not be able to use the visitor pattern, and you're going to have to use your own custom solution. So this is essentially what I have on the board here. So essentially here, this is a function definition, function f. It has a list of parameters. It has a return type, and then it has local variables, and it has a single statement here. And that's the representation of that here. As I explained before, so the processing of these here to check, for example, if ID is defined inside of the scope, and if all of these IDs are defined inside of the scope, and then if the type of this ID is the same as the type of this ID, it's basically assuming that I already have the symbol table so that I can actually verify if these IDs are valid inside of this scope. That's why we want to have different phases. In this particular case, it's possible to do both of these operations in the same phase, but I will, there will be reasons why we must have more than one phase. So you should expect, you should have a solution for having more than one phase. And the visitor pattern is actually very easily allowing you to have more than one phase. If you start piling up, I might say, semantic actions across different phases, and you're going to think that they can operate all in one phase, like concurrently, it is going to become very confusing as you're going to add more and more semantic actions. The visitor pattern, one of the advantages of it in this particular application of it is that it allows you to separate your semantic actions into groups. For example, you're going to create a group of semantic actions that are about creating the symbol tables. Then you're going to create another group totally distinct from these symbol table semantic actions. You're going to create another group of semantic actions to do the type checking. Then eventually, when you're going to do the code generation, you're going to create another group of semantic actions that are going to be about one of the phases of the code generation, and then another group for the actual code generation at the end. Okay. And then they're all going to be totally distinct from one another. If you don't have this possibility, then you're going to have to add, pile up, you're going to eventually pile up your semantic actions, and they're going to cohabit in the same solution, which is going to create some problems, of course. The visitor pattern allows you to create groups of semantic actions that are distinct from each other's group. So that's what I'm showing here. For example, you have these semantic actions here in blue that are your symbol table generation semantic actions. Okay. And then you have those in green here, which are the semantic actions that are about, for example, type checking of an expression or type checking of an assignment statement. Eventually, what you want to do is to separate them from one another so that you do first you run all the semantic actions for the symbol tables, which construct symbol tables and somehow put them inside of the nodes, so that next thing you do is to fire all the semantic actions for the type checking, which will then use the symbol tables that were put inside of the nodes by the previous group of semantic actions. So these semantic actions should be executed as the tree is traversed. So somehow what you are doing is to somehow inject new methods that are going to be called as you come upon a node here, as you do the traversal of the tree. Every time you come onto a node, you want to trigger some action. For example, this node here, one of the actions it will do eventually is to create this empty symbol table and then scan over the subtree and then grasp get or fetch the symbol table records that were created by these subnodes here and then put them all here. And then when you come here, then this one should be responsible to create this symbol table entry, which will then, when this one fires at the end, would actually get it and actually put it in the table. Okay. So depending on what type of node it is, it would actually have a different behavior and different action, different semantic action. So then you see that it's possible that there will be, depending on what phase you're talking about, then there can be different actions that would be triggered by the same node depending on which phase you're actually executing. And that's one of the things you want to avoid. You want to separate the semantic actions of different phases from one another. If your idea of your design is to add new member functions to each of your AST nodes to do the semantic actions, then you won't have a choice but to actually have them all in the same AST node. And then the question is going to be, when are they actually fired or not? So then you're going to need to have some kind of controller inside of your AST node to decide, depending on which phase, which are the methods that you're going to call in which order. Okay. So you want to avoid that. Using the visitor pattern would avoid that you have to make this decision inside of the code here. We'll see that later. So the semantic actions are triggered as you traverse the tree. Okay. There has to be some mechanism that you add that is going to, as you come into a node, that is going to fire some semantic actions. So there can be either as the node is started, as you traverse first, as you come onto the node the first time, there might be some semantic actions right away that are triggered, like for example, creating the table. And then there might be also some other actions, such as here, when you enter this node here, you create the empty table, then you actually traverse all the children. And then these children will eventually create these entries. And then when you finish traversing the whole tree and you come back here again, then you may want to fire other rules that, for example, will get all these records from the children and then put them in the table. Okay. So there's some actions that may be triggered as you enter and some other actions that may be triggered after you've traversed the whole subtree. Okay. You want to avoid these as much as possible, and especially to have both actions that are triggered either before and after. You don't want to have this distinction. Sometimes you have to do it. I believe in our language that you don't have these. I mean, semantic actions to have a node for a certain phase that need to execute things both before, as the node is first reached, and other actions that are triggered after the subtree has been all traversed. Okay, so semantic actions are triggered as the tree is traversed. Then each node may potentially have to execute 0 to several semantic actions. So it's not the case that for every phase, every node will have semantic actions. So it's up to you to figure out which, depending on which phase you're implementing, which node type will actually need to trigger some semantic actions. It's not the case that for every phase, every node needs to trigger something. So yes, it may seem that what you may want to do is to add member functions to your AST nodes. I would discourage you from doing this. It may seem to work, but as you're going to add more and more and more semantic actions further down the road, it's going to make your AST nodes incredibly complex and confusing and error prone. And then as you add something else, it's likely to actually make what you had before to stop working, in which case, of course, you're going to be in trouble. So eventually, as I said before, there is going to be some semantic actions like these here that are going to necessitate that some of the other semantic actions have already taken place, such as these here require the symbol tables to have already been done. There's often precedence between a group of semantic actions and another group of semantic actions. That's why you need to have a mechanism somehow to enable compilation phases. So for each phase, eventually there's going to be an entire traversal of the tree that does one phase. which are going to be some effect like creating the tables. And then you will trigger another phase, which will, in which case the tree will be traversed again. And then these actions will actually use the result that was created by previous actions having been executed. So the thing with the visitor design pattern is that it allows to control and it provides a solution to this entire problem. Okay. So what is the visitor pattern? So essentially it allows you to do the traversal of the tree. It allows you to fire semantic actions, and it allows you to group semantic actions. So it actually provides the totality of the solution that we're looking for. It is, I repeat, an amazing application of a design pattern. The visitor pattern is very specialized. As we will see, it's kind of complex, but it seems to be an absolute best match between the problem that we're trying to solve and an actual pattern. It's one of the best matches I've ever seen for any design pattern. So what is the motivation of a visitor pattern? So the idea here is that you want to add operations. Okay? So you have a group of classes. So when you want to use the visitor pattern, here I'm talking about the visitor pattern in general. Okay? When you want to use a pattern, that there are some specifications as to what are the prerequisites of the problem that you're describing for this pattern to apply. For a visitor pattern, it assumes that there are many different subclasses of a common class, and what you want to do is to add or inject behavior into these subclasses depending on what subclass they are. Okay? So you will inject behavior to a certain subclass, behavior A, but you will also, for another subclass, you will inject behavior B. So you will inject different behavior depending on what subclass this class is. So it's a very specialized kind of application. Yet this is exactly what we're looking for. In our case, we have nodes. The parent class of all the AST nodes is node. And each of the different nodes each have a different subtype. They are of a different subtype of node. That's exactly what we're talking about here. Plus, what we want to do is to have semantic actions. So the semantic actions are some methods, literally, I want to add to this node. And then I want to add different behavior depending on what kind of node that is, which is exactly what I just described as to what the visitor pattern is doing. Plus, the visitor pattern allows you to, okay, let's put it, let's turn the table here and describe the visitor pattern abstractly speaking. So here you want to add behavior to subclasses. Depending on what class you have, you want to add a different kind of behavior. Plus, sometimes what you want to do is, depending on the situation, you may want in some circumstance to inject a group of behavior, say a group of behavior A, into all your subclasses. And then at another time, you may want to inject other kind of behavior on the same classes. And that there would be no coupling somehow between these different groups of behavior that you want to inject in your subclasses. Also, the visitor allows you to do that. Okay. So it not only enables you to insert behavior in all of the subclasses, depending on what subkind they are, but also enables you to inject different behaviors depending on the context in which you are. So in our case, the different context of injection is going to be the different phases that we are implementing. So the intent of the visitor is to essentially inject new operations inside of existing classes. If you would do this manually, then you would have to go in the code of each of your AST classes, and then you would manually implement methods for every of the semantic actions that you want to add into your code. The more you do this, the more it actually makes your AST data structure more complex. In our case, using the visitor pattern, all this code that you're adding, it's not going to be in the AST nodes. It's going to be in another class, which is going to be a visitor class. So it enables you to keep somehow the complexity low by adding more behavior inside of your AST nodes subtypes. So it also provides you modularity and cohesion by allowing you to separate these different concerns or groups of behaviors into different visitors that you implement independently somehow of each other. Okay. So what is the structure of this visitor pattern? First of all, there's the element. As you know from patterns, they each have their own terminology. So they have the element and the visitor and the client. So what is the element? The element is the superclass of all the objects in which you are injecting the behavior. So in our case, the element is the AST node superclass. Then you have element A and element B, or the concrete elements. In our case, this is going to be the subclasses of node that we have. So element is node, and then all these concrete elements are, for example, function definition node, variable declaration node, actual parameters node, variable declaration node, an ID node, an int node, or type node. These are all the concrete elements of the visitor pattern if we want to apply the visitor pattern to our existing design. Then, but these are things that are already existing in our design. Okay. Then what you need to add in order to have the visitor is to create a visitor class and a concrete visitor subclasses. The visitor class is going to be the superclass of all the visitors. And then the concrete visitors, each concrete visitor is going to provide the implementation for one phase of the tree traversal. Okay. So we're going to have one concrete visitor for creating the symbol tables in our example, and one concrete visitor to do the semantic checking later on, as we had here. And then the client, of course, the client is this driver that you are creating that is basically receiving the AST from the parser and then essentially firing the traversal of the tree given a certain visitor. Okay, so let's go into the code here, into more of the details of the implementation. Okay, first of all, one of the things about the visitor is that it somehow is simulating what is called multiple dispatch. So the idea here is that most programming languages or object-oriented programming languages actually use single dispatch. Let me forward a little bit here. Explain this. I'm going to come back to this, but here it's explained here. So for example, well, dispatch actually means to figure out when you have a function call, what function should actually be called. Basically, it's a dynamic dynamic binding, or it's a binding operation. A dispatch is a binding operation that determines which exact function is going to be called in the case where there's multiple possibilities. Okay. So let's concentrate on this line of code here. So say you have here E1 is, you have E1.accept V1. Now, if you have single dispatch, what's going to happen is that the dispatch is going to be done according to what is the type of E1. Okay. So here you have a call to accept. As we will see, there's going to be several definitions of accept. Okay. And then for each of the different types of elements that we have, there's going to be a different number of accept functions. So then the question is, which one of all of these accepts are we calling? Okay. Now, as example, Java has single dispatch. The only decision it can make at this point is that it's going to call an accept function. And which one it is the accept function of the type of E1. So the type of E1 in this case is element 1, which is one of the concrete elements of my visitor pattern, or the subkind of AST node. So here, so depending on what AST node I am right now, it is actually going to call the accept method of this particular kind of AST node. But then keep in mind, I also have different kinds of visitors. So then this is the parameter of this function. Now, thing is that Java is using single dispatch. So it's going to only make a decision according to the type, the specific type of this here, and it's called the accept method of this here. If there are different accept methods that are defined here, especially if there's subclasses involved in this parameter type here, which is visitor, which there is different subkind of visitors, single dispatching is not going to take care about branching to the right accept depending on the subkind of visitor. Okay. There are some languages that do that, but then they would actually implement what is called multiple dispatch. Okay. Now this pattern is made, the visitor pattern is made for languages that don't have multiple dispatch. So eventually, the first decision that's going to be made, the dispatch decision that's going to be made by a Java implementation of this is going to be made according to the subtype of element on which you call accept. Then it is actually going to call the accept method, and then the accept method here is going to call another method, which is the visit method, which is going to trigger the semantic action. So essentially the visit method is the semantic action. So then here it's going to call the visit of the actual visitor that you are currently doing. So depending on what visitor you have triggered, then this visit here is going to call the right methods. It's going to inject the right method for this particular visitor at this particular time. Okay. So this is the issue about single dispatch. Because Java uses single dispatch and because the visitor pattern assumes that the language that you are using has only single dispatch. If you are using a language that has multiple dispatch, the visitor pattern is going to be different from that. Okay. So close parenthesis for that at this point. This is an interesting aspect, of course, because we're talking about programming languages here in this course. So it is possible to have multiple dispatch, but the point is that the way I described it here, it's not extremely simple, it's not simplistic, but it's not difficult to figure out. So you might say, why is it that multiple dispatch is not implemented in all languages? Fact of the matter is that if you're trying to generalize multiple dispatch, it opens the door to so many different cases down the line that it's like opening Pandora's box or something. So multiple dispatch is kind of a simple concept, but not in the general case if you want to have an implementation for everything. It actually makes it pretty complex at runtime if you want to have multiple dispatch. That's why most object-oriented programming languages don't have it, because it induces complexity and computation time to dispatch any function call hereafter if you have a multiple dispatch implementation. So here, visitor pattern assumes you have only single dispatch and is actually simulating multiple dispatch using 2 steps of single dispatch. Okay, so close parenthesis on this. So eventually what we want to have is to have, for every kind of my nodes here, I want to implement semantic actions. So my visitor class is actually going to allow me to create semantic actions for a particular kind of visitor. Now, my superclass of visitor classes is going to be looking like this one here. So essentially for the visitor class, I'm going to have one visit function for each of the different subkind of nodes that I may ever want to have a semantic action for. So you might as well have one visit function for all of your node types in the superclass visitor. So that when you're going to create a subclass, then you're going to pick and choose those that actually have some behavior to implement a semantic action for this particular visitor, that your concrete visitor that you're now implementing. Now, what I did here, as you see, it's quite unusual. I created all my visitor methods and I made them empty. Okay. Why did I do that? Because essentially I'm creating default empty behavior here. So when I traverse the tree, that if at the subclass of visitor level, if I don't implement some semantic actions for a certain subtype, then what it will do, it will fire these methods here, which will do nothing. Okay, so that's because when you have abstract classes, it becomes more restrictive. That's the solution I chose for my implementation. Some people might argue this is ugly. This is the choice I made. So the visitor class can be an abstract class, or it can be an interface, as you wish. But depending on what decision you make, it is more or less restrictive. That's the particular decision I made. So here I have actually these here in order to provide default behavior in the case one of my concrete visitors is not going to implement a behavior for a specific phase. Because I remind you, in a specific phase, there are some nodes for which you will traverse them, but there will be some nodes that will not trigger any semantic action. For example, when you traverse the tree here, if you are building the symbol tables, then this node, this node, this node, this node, and each of these here will trigger semantic actions. However, when you come here in the statements, there's going to be nothing to be processed here. There's not going to be any semantic action triggered because these do not define anything that require to be put inside of the table. Okay, so traversal is going to be done, yes, but there's not going to be nothing happening. There's not going to be any semantic action triggered. Then I go and implement my concrete visitors. These are going to be subclasses of my visitor class that I had in the previous slide. I remind you that concrete visitor, you create one concrete visitor for every phase. In our case, you're going to be a concrete visitor for creating the tables, another separate concrete visitor to do the semantic checking. So you see here, what you do is basically for every type of node. Here, this is a semantic action for the variable declaration node. So that, for example, is like this one here, these two here, right? And then this is implemented as a visit member function of my concrete visitor symbol table creation visitor. So essentially, this visit method here is going to be called eventually, as we will see later, it's going to be called every time I come into a node like this. Eventually, the visitor is going to call visit of this node here, which is going to trigger the execution of this function. Essentially, a visit method is the procedure that's going to be executed by a semantic action. Visit method is a semantic action. So for every of the node types which need to have a semantic action in a specific phase, you would have a visit for this specific type. If you don't want anything to happen, you just don't include anything in this concrete visitor. And then what's going to happen if you do that, then this method at the superclass level is going to be executed, which does nothing. Okay. Okay, so what does it do? For example, here, variable declaration node visitor for the symbol table creation visitor. So essentially here, one of the decisions I made in this code, by the way, this code is in the, well, let me show you. This code is here. Sorry about that. This code is here. So in next week, there is in the lab, there's going to be an explanation of what I'm explaining right now, but hopefully more details. So the visitor of all phases, you go here, there's going to be a Java code here, and that's basically the implementation of what I'm showing on the slides. Okay. Okay. Okay, so let's continue. So here the decision I made is that as I process a node of this kind, then my symbol table record, as I was explaining here, there's a symbol table record that is being created as I traverse this tree. In my case, I made it very simple. My symbol table record is essentially I aggregate the information into a string. Okay. I don't advise that you do that. It's going to make things more complex later on, but I try to make it as simple as possible so as to not create a larger amount of things to be have to be explained. So all this to say that here I'm aggregating information about my variable declaration. Well, first thing is it stores what is the kind of variable we're talking about. Here it's a local variable. So you see, I'm just basically aggregating all the information inside of this string here. Then I actually go into, so this, for example, will aggregate information as to what is the type of the actual variable. So you see here that my children, here I have 1, 2, 3 children of this node here. So you see I'm referring to them as get 0, get 1, get 2. So my children here I essentially stored in an array of nodes. Okay. Again, simplified solution. So here I'm actually getting the name of the type of this variable. For example, like in this case, int. So then I would be aggregating int after local var by this here. Then next thing is I actually go at this node here, get the name of the ID, and then put it inside of my symbol table record, that is a string. Then here, I'm actually going over the list of children that I have here, which is a list of numbers, which is the list of dimensions of this variable if they ever exist. So I go over here, get, for example, 2 and 3, which is the dimensions of this variable, and then I actually push them inside of my string here. So then after that, my string contains a colon separated list of numbers, a list of strings, which then I will eventually assume is a record that eventually is going to be put in my table. And now important that you see that okay, yes. In my node, Now I have to actually create a new data member, which is a symbol table entry, because this node here needs to actually contain this symbol table entry. Okay. So that's one of the things I have to add to my node data structure. I need to add this data member that is a symbol table entry that a node might actually contain. Okay. That means you need to add some things, yes, to your AST data structure in order for this particular kind of action to take effect. Okay. So after the end of the computation of this semantic action, my variable declaration node will contain a symbol table entry for that contains aggregated information about all the children node of this variable declaration. Then eventually I will have a semantic action at this level here that will pick up this node here, this symbol table entry, and will actually put it into the table or put a link to it into the table, a reference to it into the table. Okay, so that's for the visit methods. Again, visit methods are the semantic actions. Okay. All your semantic actions that you will ever design using the visitor pattern, they're all going to be in a visit method for a specific kind of visitor or a concrete visitor, and for a specific type of node. That is, it's going to be this semantic action here is going to be triggered when you traverse a variable declaration node in the symbol table creation visitor phase. Okay. Then the other counterpart of this is what is called the accept method. So you see here that here, this is the visit method is assuming that it's going to be called somewhere. So what is this somewhere? Somewhere is actually when you call the accept method, counterpart of the visitor pattern. Now, this is where you actually have to add inside of your node class. You have to add this accept method for every of your different kinds, so that every of your different kinds of nodes will be able to call accept. Accept is going to be the method you're going to call to tell a node that eventually it's going to traverse, be part of the tree traversal, and that it will eventually call a visit method. Now, for example, for a leaf node, if you are in a leaf node, then eventually the tree, what is the tree traversal you do when you are at a leaf? You don't have any children. So the only thing that you will do is to actually call visit, which is going to trigger the potential semantic actions that is implemented in this particular node for this particular concrete visitor. Okay. So the tree traversal business of any leaf node is just to call visit because they have no children. If they would have children, then they would have call accept on their children before they call visit. And that's exactly what this is happening here. For any of the intermediate nodes that are not leaf nodes, what they do is they force their children to actually accept the visitor. Then after they will have called accept to each of their children, which will then call accept of their children and so on and so forth, until you reach leaves, in which case the accept will start to resolve, and you come back and so on. It just basically will do the depth first search traversal of your tree by calling. You will call accept on the superclass on the parent node, which would then call accept on its children, call accept, accept, accept until you reach the leaves, in which case it's going to resolve and come back to the parent. And this one's going to call accept, come back to the parent, accept, so on, called back to the parent until you actually have traversed the whole tree. Okay. Then eventually, after a node has called accept to has forced all their children to actually accept the visitor, then they will actually call visit in order to do the semantic action. Okay. So you see that if you have an intermediate node, then they call accept. They force their children to accept the visitor. And then after all their children have accepted the visitor and eventually called their own visit, then you actually call visit yourself as the parent. That's how eventually this one here, after it has called accept on all its children and so on, eventually these children here would have called visit and created these semantic, table entries. So there will be, as a result of this process here, there will be a symbol table entry here and here and here, so that eventually after this one has called accept on all its children, it will come back here and then we'll call visit. And then their visit method, what it will do is we'll pick up all these symbol table entries and then we'll put them in its own table. This is how accept is, so repeat, accept is what is doing the depth first search traversal of the tree, plus actually triggering the semantic actions if they exist. Eventually, your whole driver of the whole thing, so that's the thing that will actually, well, first of all, call the parser to create the AST, and eventually as it will get the AST, it will create a visitor, and then will actually force the root of the tree to accept this visitor. Then this root of the tree will force accept on all its children. Eventually they will all be calling visit, and it will come back, and then eventually all the semantic actions would have been triggered. Okay. So essentially, that's what's happening here. So here I'm creating two different kinds of visitors. And then I'm creating this node data structure here manually in this case. So, and then on top of my tree, what I have is my my plus node. Okay, because here I have d plus e times f. So the top node is the plus node. So then I actually tell my plus node, which is the root of my tree, to accept this visitor here. So what this visitor here, that's again some code that is in my example code. So this construct expression string visitor, what it does is basically it outputs, it creates the string d plus e times f by traversing the tree. Okay, so it's somehow recreating the program by traversing the tree. Okay. Eventually, I have a more elaborated version of this in the code, which is in fact recreating the program by traversing the tree, rewriting the program by traversing the tree. You don't have to do this one, but it's just a nice example to show. And providing yet another kind of visitor as an example. And then there's a type checking visitor. So you want to check if, for example, d plus e times f is type valid. In this case, it would be not be type valid because f is float and the other ones are int. And we only allow operations on all the same type. Okay. So this would eventually output d plus e times f by the operation of this visitor here. And then eventually it would output a semantic error saying that operation times involves two operands which are of different types. So you see here, created my tree data structure as nodes. Then inside of my nodes, I have included the machinery for this to work. And then I've created these two visitors here. And then eventually I'm calling accept of these two visitors. And then successively, I'm traversing the tree once with this visitor. And then once this is finished, then I call accept again on this tree. This tree will be retraversed again with another kind of visitor. And in this other kind of visitor, there's other implementations for visit, so that when it will traverse the tree in the same way, it will execute different semantic actions, totally unrelated to the previous execution of the previous visitor. So this is where I describe as I did before. So I'm going to go quickly this time. So this is basically implementing a double dispatch. Okay. In general, what you may want to have in the programming language, if you implement more than single dispatch, is to have multiple dispatch. Here, this is implementing only double dispatch, which is subkind or elementary kind of multiple dispatch, or one specific kind of multiple dispatch. Okay, so first of all, what you want to do when you call accept is that eventually it's going to call visit. When you force this node here to accept, what you want eventually to be called is the right visit method, both for this kind of node and for this kind of visitor that you have. Okay, so that's basically requires double dispatch. As I've explained before, languages that Java have only single dispatch. So that's why in the visitor pattern, there's this two level of processing. You call accept, which then calls visit. One dispatch by accept, by calling accept, and double dispatch by calling visit inside of accept. So that's how it achieves double dispatch mechanism. So again, here, you have this, the client here is describing this element. Again, this is the code that I have here. So this is the element. So essentially my element here that I'm calling the visitor for is plus, which is the node, which is, it's a node, plus is of type node, but I instantiate it with a subtype add up node. So essentially here, plus is of type node, statically speaking, but dynamically speaking, it's of type add up node. So compiler knows that plus is of type add up node in this case, but then, and then we'll actually call the accept of this type here. Then the other part of the double dispatch would actually be that it would actually call the right visit method depending on what is the type of the visitor that I'm having. So this is the first part is here. So I have my element here, which is my node type. This is my add up node here. And then I define my visitor that I want to fire. And then I call element.accept visitor. So at this point in time, the only thing it can decide is what accept method it's going to use. So it's going to call the accept method of the element one type. So then it's going to fire this method and pass this visitor one, which is this visitor one object here, but my parameter is of type visitor. Okay. But then when it comes here and executes this method here, then dynamically at runtime, it knows now that this visitor here is actually of type visitor one. That's why when it calls visitor.visit here, it knows that this visitor is of type element one at a runtime. So that's why it will enable it to be able to call visit of the right kind of visitor. That's how it actually does this double dispatch. Okay. Again, if you would be using a language that is using multiple dispatch, then it would be organized in a different way. Okay. So so in this way, the subtype specific behavior of element on element is actually triggered. So that's what we want. So we're calling, we're telling a certain node of a certain subkind to actually trigger some semantic action that depends on what subkind of type it is actually. Okay. So we want to trigger subtype specific semantic actions. So that's what this pattern enables you to do. Plus, as you implement your visit method in each of their different visitor patterns, then that allows you to implement them separately from one another by creating different subclasses of visitors, for one for each of your different phases. And that allows you to separate your phases from one another as much as possible. Both of these things is what is makes the visitor pattern absolutely fantastic for the job that we have to do. Of course, in our case, the elements of the visitor are AST nodes. And then for our concrete visitors, eventually we will have need to have a concrete visitor for the construction of the symbol tables, and then for the type checking, and then for the translation into executable code. And if we would have optimizations, eventually we'd have further visitors for the optimization. In a real-life compiler, there is actually a lot of different optimization phases after the code has been, before and after the code is being generated. Real-life compiler has dozens of phases. We will have 1, 2, 3, maybe 4. In assignment number 3, there's actually 2. Okay. So what are the visitors? How do you organize your code for the symbol table creation? So you want to figure out what is each of the different scopes, first of all. So for example, here I've defined that, I've identified that function definition node represents actually all the function definition node and its subtree represent a scope. And then for each of the nodes that actually represent a scope, it will eventually contain a symbol table. Okay. Then you have inside of these or below these nodes that represent a scope, inevitably you're going to have some subtrees. For example, here that represents a variable declaration that will itself contain a record that eventually will become part of the table. Okay, so that's what you need to figure out. What are the different kinds of nodes that represent a scope? And then inside of these, what are the different nodes that represent entries in the table? Then you will need to implement semantic actions, as I described before, that will, at this level of node, will create the symbol table record by traversing the tree here, as I explained before. And then you do that for every node that represents, that creates a symbol table record. And then eventually this one will first create the table and then fetch all the records from its correct children and actually fill the entries inside of the table. So that's it for a higher level or more complete program. So at the program level, you actually will, the prog node will have to create the table and then fetch the records from their children here. For example, the prog contains class. So it will eventually create this table and then fetch the entries for the classes and put them here. And then it will fetch the entries for the free functions and then we'll put them here. Then the class declaration subtree will contain its own symbol table. So the class declaration node will contain a link to this or a reference to this table. And then eventually the member list of the class declaration will each contain, if they are a function, then they will contain a symbol table as well as their symbol table entry in the class level. If you would have members that are variable declarations, then they would only contain their symbol table record, which would then be added inside of the class table by the operation of the semantic action at the class declaration level. Okay. So you see that this process I described before can all be generalized to have everything you need to have in order to create the symbol tables. Exactly the same concept, but applied to at different levels. Same concept as I described before for this example here. So here you have, this is your symbol creation visitor. That's the visit method, so the semantic action for the prog node inside of the symbol table creation visitor. So that's the semantic action for the prog node. So first of all, it when you visit this node, when you fire this semantic action, it creates the symbol table that is associated with the entire program or the global symbol table. Then what it does is actually it gets the symbol table entries that were generated by some of its children. What are these? That would be for example here, children.get0 of prog is the class list. So essentially this loop here loops over the children that are classes and then gets the entries that are generated by each of the class nodes, and then takes them and then puts them inside of the global table. Then it does the same for the actual function definition list. So get1 is actually this child here, which is a list of function definitions. So it gets all the children of the funcdef list child of the prog node. So basically it gets all the function definitions that are defined inside of prog, or all the free functions that are defined inside of prog. It loops over all of them, gets their symbol table entry, and then puts it into the global symbol table. Then, okay, and then the stat block here for prog is essentially your main function. Okay, so the global symbol table has a sub symbol table or a sub scope, which is the main function scope. Because the main function, when you execute it, it should have access to the actual global symbol table if it ever uses IDs that are defined at the global level. So that's why it needs to be a link between these two. And that's how you do this link here. So example, node prog dot get children get2 is the actual statement block node of your main function. And then it gets the symbol table of this statement block and then actually names it program and then links, adds this symbol table entry into the global symbol table. Then if it's basically exactly the same kind of process is happening. So a symbol table creation visitor for the class node. So in this case, class node, it loops over all its children and essentially it gets, creates its own, no, okay. First of all, it creates the symbol table for the class declaration. Now, what is the name of this symbol table? It's this name that is stored here. So first, it gets this name that is stored here in order to be able to create this symbol table, which has this particular name, which is the name of the function. Then what it does is that it loops over all its children, and then it tries to find children that actually define a symbol table entry. That's what it does here. If you loop over all the children, if the child has a symbol table entry, take this entry and then put it in the table. And then this class declaration needs to be an entry inside of the global table. So it has its own symbol table entry. Because keep in mind that this prog here actually got this symbol table entry from the class list. It's here. Okay. So essentially, this one will be executed before this one here. Then the same thing will happen for a statement block node. In this particular language that's being processed here, inside of a statement block, you could have a variable declaration. That's why statement block is a parent of statement or variable declaration. A little bit different language. So basically, the statement block node, again, loops over all their children. And if they have an entry, that would be only the ones that are actually variable declarations. If they have an entry, then you take this entry and put it into the symbol table of this statement block. Now, this is how you do the creation of the symbol tables and all the levels and so on. And then you end up having subscopes for classes and for function bodies, either free functions or member functions. And then the function body has their local variables that have parameters inside of their own table. So when you visit any of these here that represent a scope, then you create the symbol table record for this scope. And then you let it get the records from its children and put it in this table. And then you create this symbol table entry for this subscope so that it can be picked up by the program node at the global level to make this sub table for this subscope be a record inside of the global table. And then eventually at the bottom here, you actually have a variable declaration node that is in either of all of these subscopes. So then eventually, and this is the one that will create a symbol table entry, as I actually described here previously in the beginning of the lecture. So here, the symbol table entry is this string here. And basically, I'd already described this in a previous slide. So I'm storing, this is a local variable. Then I get what is the type of this variable, what is the name of this variable, and what is all the different dimensions, numbers for this particular variable. I'm all storing this into a data structure and then storing it as a symbol table entry inside of the node or the variable declaration node. Thus, after I've been finished processing this subtree here, I have attached to this node this symbol table entry record, which is then going to be picked up by this one here and then put into the table. So how do you do the AST visitor for semantic checking? Basically here, that was about symbol table creation. Now you need to somehow repeat the same thing, except that now you had designed your, in the previous slide, I shown how you design your, what was the name for it? Symbol table creation visitor. Okay. And you created all these visit methods that implement each of the semantic actions to do the process I was describing here. Now, after this is finished, you will never touch that again. It's going to be basically its operation, the result of its operation is going to create these symbol tables. Then you create another visitor that is going to take for granted that these symbol tables are already there. Okay. So you see that there is some coupling somehow between these different phases, but it's kind of an indirect coupling. They're not directly using one another. They are somehow indirectly using some of the results of the operation of the previous phases. Now here, this is describing briefly how you can do the another visitor, but for the semantic checking. There's a lot of things that you might want to do, that you want to check as semantic checks. For example, multiply declared identifier. As I said earlier, this will actually be checked during the symbol table creation. If there's more than one identifier with the same name that's going to be created, they're going to end up having two different semantic symbol table records that are records for a variable with the same name. So when you're going to actually end up trying to add it to the table, you should detect that you cannot have two elements in the dictionary which have the same name. Thus, you will output an error message. So you see that there is some of the semantic checking that is going to be done as you're doing the table creation. Things that you did not do as you were doing the table symbol table generation phase is to check in the statements when you are using these IDs. You could not check if they were actually properly used. Okay. So, for example, undeclared identifiers. That's one of the things you're going to do in the semantic checking phase or visitor. So as the program actually refers to IDs, then you have to check if these IDs are defined in this scope. How do you check it? By looking up in this particular scope's symbol table. Okay. This I already described before when I described the operation of the symbol table. If you check up in, let's say, you refer to variable X here in this particular scope, you look up in the table. If it is there, then it's correct, it's defined. But if it's not there, you also have to check in the superscopes or the enclosing scope of this particular subscope here. So you need to have this, the lookup to a table needs to jump to the parent table. That's what I'm explaining here. Then there's eventually type checking. So if you have X is equal to A plus B, you have to check that A and B are of the same type. And then you have to check that the resulting type of the multiplication of these two things is the same type as the left-hand side of your equal operator. Okay. So you have to check if operators types are invalid, if the type of expressions passes parameters do not match the function's parameter types. The type for an assignment statements right and left hand side do not match, or if the return value in the value returned, returned by a return statement is the same type as the type of the function to which it belongs. So here are two examples of a visit method or a semantic action. This is semantic checking to actually check whether or not the two operands of an addition operator are actually of the same type or not. And then would actually also infer what is the type of the plus expression. Okay. One thing that's important to realize here, if you want to check if the type of the left-hand side and the right-hand side of the expression are the same, you need to know what is the type of the entire expression in order to check if the type of the expression is the same type as the left-hand side of the equal operator, the assignment operator. That means you need to have, let's say you have ID times ID, then you need to infer what is the type of this ID times ID operation. So what is this type? That's what is explained here. So essentially what it says is that if the type of this and the type of this which you must look up in the table, type of this and the type of this is the same type, then the type of this here is the type of either of these. Okay. If it is not the same type, then you should output a semantic error, such as I have here, right? So you see here that there's two visitors, one for the add operation node, multiplication node. There's eventually one for the assignment operator node, and so on and so forth. So this is how you do the semantic checking in another phase by implementing another visitor. So then you're going to have two different phases that are going to operate. And I can reiterate that this phase actually requires the previous phase for having already operated because it is using the simple tables. So eventually you're going to have to implement more than one visitor for each of the different phases. In the example code I gave, there is a symbol table creation visitor, a type checking visitor, and as I explained before, a construct, assignment, and expression string visitor that is basically recreating the initial program as it is actually traversing the tree. This one you don't need to have, but I just thought it was a nice example to have. So that's it for this lecture. So see you around. Thank you.